Hello, everyone. My name is Martin, and I'm going to be presenting our paper, Endangered Privacy, Large-Scale Monitoring of Video Streaming Services. Um, in this work, we show that a man-in-the-middle eavesdropper is able to tell exactly which video you're watching on large streaming services, even though the stream is encrypted. So let's start talking about modern video streaming. So back in the day, we used to have UDP-based protocols such as RTP. However, streaming wasn't very efficient. So today, streaming is all HTTP-based, and we call it adaptive bitrate streaming. This means that videos are encoded at multiple bit rates and split into segments, usually between 4 and 15 seconds long. The client will initially fetch a manifest file to facilitate the stream, and this is to be able to locate available qualities and segments. So to be efficient, we use something called variable bitrate encoding to encode videos. So if we have like a fixed amount of allotted bits, we don't want to waste bits on low entropy scenes. So for example, a scene with a mostly stationary speaker would have a low bit rate, while something like confetti, where everything on the screen is moving, that would have a high bit rate. And now a consequence of using a variable bitrate encoding is that we get variable sized segments. And these become sort of a fingerprint for a video. So here I've plotted out the fingerprint for the first episode of Friends on the Mac streaming service. So just to get an idea of how a fingerprint looks like. So in a nutshell, adaptive bitrate streaming is just downloading and playing these segments, usually with some delay between requests. So a common strategy would be that you request a new segment when the buffer goes below some threshold. And what this means is that we get a very bursty network pattern, as you can see here. So you would have something like you request a new segment and you get a new burst like this. And this bursty network pattern essentially becomes a leak, since we can correlate the size of a burst to the size of a segment of a video. And the sizes of consecutive bursts can leak the exact video being watched. And there's been previous work on this. So in the current landscape, or where the research stands right now, is that attack has been shown to work. And generally and very broadly categorized, there's two schools of thought here, machine learning and fingerprinting. So in machine learning, we train a model or a classifier on live captures of a certain video in order to have that classifier predict the correct video. While in fingerprinting, we make use of the segment sizes we have collected beforehand, and we have some sort of heuristic to figure out which video is being played. However, previous works are largely impractical to apply in real life scenarios due to small data sets, base rate neglect, costly data collection, or simply requiring specific network characteristics. So the goal of this work is to demonstrate that the attack is not only possible, but it's practical to deploy for monitoring of entire services. We have collected the largest dataset of monitor videos by far, around 240,000 videos with 3 million fingerprints. And this is facilitated by our efficient data collection method that I will explain later. It is also protocol agnostic. We aren't relying on specific network characteristics. For example, it even works when the target is using VPN or over passive Wi-Fi sniffing. So let's look at some of our evaluated attack models. So first, we have the strong attacker. And this mimics the most typical or normal scenario where the target is not using a VPN and it's just streaming over HTTPS or TLS. And here the attacker, like your ISP in this case, can isolate the video stream, like either by keeping a lookup table for known IP addresses or by inspecting the TLS handshake to get the SNI or server name indication. for example, like Prime Video. Then we have the weak attacker, where the target is using a VPN to master traffic or a VPN service. Here, the attacker would have to deal with noise, as it wouldn't be able to isolate the stream in the same way. But however, like in this work, we assume that the target is not actively doing anything else other than watching the video. For example, we assume that the target is not web browsing, but like other background traffic, such as ad and telemetry data from the stream itself or background application, will still contribute to noise. So let's go over the attack. First, we need to collect data. And for this, we have a dedicated program that obtains fingerprints for all video encodings. This program leverages the manifest files obtained at the start of a stream to find the sizes of all segments without ever having to stream the video. And with this program, we obtained all videos from Amazon Prime Video, Max, and the Swedish video service SVT. And it takes the program less than a day to collect all these fingerprints. And it shows that data collection is not a bottleneck for this attack. For example, you could run this program every day as libraries on these streaming services evolve to always have an up-to-date data set. Next, we organize the collected fingerprints into smaller sequences of 8. And we store these 8-dimensional points into a KD tree, which is essentially like a binary tree for multiple dimensions to enable quick nearest neighbor searches. We can imagine it as a sliding window going over a fingerprint and storing each sequence in the tree. And this enables us to quickly search and obtain candidate videos. And the tree has a lot of points, about 2 billion points, but it's still quite quick to query it. Uses quite a lot of memory. Now for the live part of the attack. Here we have created a T-Shark wrapper, which is like the terminal version of Wireshark. And it simply sums up bursts of network traffic. These bursts correlate to the segment sizes like actually downloaded by the target as they stream a video. And the bursts are used as input to query the KD tree and retrieve candidates. So an easy way to think about it is, for example, if we have a 3-dimensional tree, it would be like querying something in a room. So you see which of your inputs are closest to other points in the room. As for the identification method, like finally, the KD tree only gives us candidates because we cannot be confident in a single query because we have low entropy or noise. So here we have a heuristic that on a very high level works by the fact that the correct video should appear more often and with a closer distance than other videos. The system will then predict the best scoring video in each time step. So a time step would be something equivalent to the request frequency, like 4 seconds, for example, when we get a new burst. And the system would predict the best scoring video that is above a set threshold theta. So here we can take a look at how the system behaves over time. So here we have a target that is streaming 3 consecutive videos from 3 different platforms over 30 minutes. And we are capturing this network traffic live as the target is streaming. So here we can see how the system behaves. So initially the target is streaming video from Max. We can see that the system is getting more confident that there is this specific video. When it's above 2.2, it will say that this is the video that's being streamed. And then as the target switches to to a video from Amazon, the score for the Max video will decay, and we will see the system becoming more confident that it's the Amazon video. And then the same will happen for the SVT video. so we can see how the system adapts when the target switches video. As for evaluating our system, we wanted to do this in an authentic network environment. So we set up a LAN with the man in the middle positioned behind an access point that 3 target devices that we call a Linux and a Mac and a Windows laptops are all connected to this access point. These targets then streamed random videos from the monitored services for 10 minutes before switching to a new one. And we have an automated WebDriver script running on all of these machines to make this efficient, but to essentially pretend that you're a real person. So the results, they show that the attack is very effective, having 99.5% accuracy after 10 minutes of eavesdropping, 0 false positives for both the HTTPS, i.e. the strong attacker, and the VPN setting, the weak attacker. We also evaluate the Wi-Fi setting. It behaves similar to VPN. However, due to limitations in our own monitoring device, we missed a lot of frames during capturing, which gave us worse results. This only happened for Amazon videos, which have a very large buffer fill in the beginning, which would overload our monitoring card. For VPN and Wi-Fi settings, we have to consider the base rate, because now we are inviting essentially the set of all internet traffic here, which could cause false positives. So this is something we discuss in the paper. Now, for mitigating the attack, perhaps the obvious solution is to simply manipulate traffic, i.e. like add noise to the traffic. And we evaluated such a solution from the VPN company Mullvad, and it does effectively stop our attack, but it's very costly, approximately 2.2 times more data use. And we believe that the leak is inherent to ABR streaming itself. And this is where the solution should lie. We cannot expect everyone to use a third-party solution. And our mitigation strategy revolves around the way the buffer is managed. And we can read more about this in the paper. Now, to conclude, we have shown that we can monitor entire video streaming services in a very practical manner. VPN does not offer full protection against the attack. And finally, we urge streaming services to address this leak as fast as possible. Thank you for listening.